and today I will talk about how to verify non-terminating programs with IO and F***. And the goal of this work is to have a practical way to verify functional correctness for high-order non-terminating input-output programs. And also, as part of the goal, is to verify a web server, a simple web server. And that's because web servers are perfect applications. They don't terminate. They're expected to run forever. And then they can also make a nice case for non-trivial IO trace properties. And what to expect from this presentation is that we use F***, and this talk is mostly about how to do it in F***, but the ideas should be general. We use monads to do verification. So we have a monad for verifying terminating programs and a monad for verifying non-terminating programs. We don't limit ourselves to partial correctness. We try to reason about non-terminating runs by using infinite traces. And also to verify our web server, we mix verification of termination programs that terminate and verification of programs that may not terminate. So why F***? I mean, other people verify the web servers in other programming languages, but F* has a few advantages. One is that we can write the web server, write the specification of the web server, and verify that the web server respects the specification all in F***. Also, F* has a feature that lets us define effects with specification. So the two effects we defined are so we define two effects, and also it hides the binds and returns. So the syntax of the web server is pretty nice. Also, it has built-in support for verification of higher order. So even if our web server accepts a function as a request handler, we don't have to treat that in a special case. And most importantly, F* has some automation capabilities. More exactly, it has SMT-based automation. So a part of the proof burden can be relieved by the SMT, so the verification can happen faster. And I told you that verifying terminating programs, we verified our web server by also verifying terminating programs. And actually, to verify non-terminating programs, it seems like we can extend our monads from terminating to non-terminating. So I will start with this. And well, to present a web server is too much for slides, but I have this small example. It's the echo program. It's not exactly the echo program. So it accepts a file descriptor, and it reads from this file descriptor and writes back to the file descriptor. So this is just an example to show you some interesting things. And we want to verify this. And so we want to verify its traces. So what is a trace? We heard about but a presentation ago, but I repeat it. So for each IO primitive, read and write, these produce an event. And each time the program runs, it creates a different trace. So possible trace is this, where it produces a read, where it reads a hello from the file descriptor 1, and then writes back hello to the same file descriptor. And an echo program any program actually produces a lot of traces, probably an infinite number. And we say that the program respects a trace property if all its traces respect the trace property. For example, this is a simple trace property that says that all the traces of echo terminate. And one more precise trace property is this one that says that the traces of echo are exactly two events, a read and a write from the file descriptor given as argument. Yeah, and the message read is also the message written. So let's look how to verify in F* this property about our program. And in F*, the specification is part of the type. So here, the specification of echo is also, it's in the type. So we can see, if we look at the type of echo, that now echo is in an IO computation in the IO effect, it has a precondition and a postcondition. The precondition is over a history of events. So this is the events that happened up to calling echo. And we can write a predicate, and here it says that the file descriptor we use, echo accepts, it must be open already. And the post condition is over also the history, the result in this case will be unit, and the local trace. So this are the events produced only by echo, or the part of the trace produced only by echo, and is the trace property that I showed you earlier. And yeah, F-star can prove this automatically using the SMT. So how it does that? Well, it's based on how effects work in F-star. And effects in F-star actually mean the extra monads. So what is the extra monad? So the extra monads are monads that are indexed by a specification monad. Here in our case, our specification monad, well, it's actually a weakest precondition monad because, well, F-star internally uses weakest preconditions, but it's very hard to think about them, and we use pre and post. We can see the type of the pre and the post, and we can also see that they are like the type of the trace is the type of the finite trace. The return at the extra monad level is indexed by, or is specified by return at the specification level. Right? So this is the specification of return. The specification of bind is the binding of the specifications. And also we have actions that also have specification. By actions, we understand open file, read, close, accept, select. Here is the specification of read written as pre and post. So the specification of read is that the file descriptor given as argument must be open, and the local trace produced by read is exactly one event, and that is a read. Right? So it's really precise. Okay, so by using the extra monad interface, F-star verifies our example. So how it does that? Well, here the binds and returns are hidden, but it uses the binds. Here, applying the bind of the extra monad, it obtains the specification of this code by binding the specification of read and the specification of write. And then doing dependent type inference, it has to check that the specification of this code is implying the specification written or given. And then this verification condition is created, and internally F-star unfolds this and sends it to the SMT, and the SMT can prove that this automatically, that this verification condition holds. So I showed you how F-star uses the extra monads. I will show you now how we define our own extra monad to verify terminating programs. And actually here we use a paper called Extra Monads for All that is done by Maillard et al. Actually, Kenji and Daniel, part of the authors, are here. And they show that we can obtain the extra monad if we have a computation monad. And by computation monad, we understand like without specification, and the monad morphism between the two, where here, to give intuition, this is like a semantic interpretation. And by having all these three components, we can create the extra monad using this representation, where the computation monad is refined by this property. And what this property says is that the semantic interpretation of the computation must imply W. That's from here. Right? So here, this monad morphism lifts the computation from the computation level to the specification level, and then it compares that with the specification from here. Okay. So in our case, we instantiate, we choose our computation monad to be the free monad. And yeah, I mean, it's just a free monad parameterized by a signature. It has two constructors. One and call is accepting an action, arguments, and then a continuation. It should be standard. And for the semantic interpretation, so again, this leaps from the computation level to the specification level. So it takes, so for a return, it uses the return at the specification level. And then for the call, it binds the specification of an action or the current action with the specification of the continuation. So yeah, so we used this IO effect to verify most of our web server. And because most of our web server has terminating parts, and we actually verified even the loop body because it's a terminating loop body. But yeah, the only thing left out is the loop. So let's look on how to do that, how to verify the loop. And here is like, again, a simple how the loop will look like it will be a repeat of the loop and the argument, the repeat of the body of the loop and some argument. And some limitation here is that F star does not support coinduction. So what we would like to have, so this is not code that works in F star, but to give you intuition, what we can like write in ML is to have an iter that accepts a function and the first set of arguments. We call this F with its arguments, and if it's a left, it means that F returned a new set of arguments. So we call again F with that set of arguments. But if it's a right, then it means that F returned the final values. So we are done. So this is for this supports termination and non-termination. And actually, to accommodate non-termination, we extended our free monad with just this constructor, where it has the same F here. It also has the first set of arguments, or at least a set of arguments, and the continuation, because repeat here can be written using iter. So I mean, this repeat here, it can be written using this iter. Right. So we change our computation monad, and we also have to change our specification monad and the monad morphism between the two. And now our post condition, right before it was over finite traces and the result, now is also over infinite traces that are represented as stream of events. So this is how our specification monad changed. And for our monad morphism, to interpret iter, we bind the specification of iter with the specification of the continuation. And the specification of iter, this is approximation. It binds, so for each iteration, it adds a tau. So tau is a silent step. This is inspired from interaction trees and extra monads forever papers. And this tau will appear on the trace like this. Like it will be, so as in our example that does a read-write and read-write. Now it will be a read-write tau, read-write tau, read-write tau. And this makes sure that our our iterations are productive. They are producing events on the trace. And this is important. Right. So now we can define IODIV for potentially non-terminating programs. We have the same precondition, but now we can write as a post-condition that our program diverges, and also that our run should be equivalent to something like this up to taus. And this doesn't automatically check yet. I mean, the part that the run diverges, it is automatically proven by the SMT, but this one is not. And this brings us to another point, is that the verification condition must be tuned for the SMT. So some of the things we've done is that, for example, keeping the history backward simplifies the verification of preconditions, because it's much easier for the SMT to look at the first event on the trace than to process it completely. Sometimes giving too much information to the SMT, it confuses the SMT, or it tries to do too much and it gets timeouts. So making things abstract is also an important thing to do. And recently we changed the specification of bind, and this simplified by a factor of 4 the number of goals in the verification condition. So this was a huge improvement for our case. Right. So how do we? Okay. So clearly, this non-terminating effect is not as friendly with the SMT, and we will not want to use it to verify terminating parts, because we will not get the automation necessary. And this is why SR has another feature that's nice, is that we can use sub-affecting. And we can use sub-affecting if we can define a lift from our terminating from IO to IO div, so from terminating to non-terminating programs. And actually, in my example I showed you earlier, there is a lift that's done automatically, because the echo is in the IO effect still. It's the same echo I showed you on the first slides. But then FSTAR lifts that to IODiv to be able to give it to repeat and to be able to write this loop echo. Right, so some conclusions. The extra monads with free monads seem fit for this task. Actually, this work started as a case study for the extra monads to see if they are practical to verify bigger projects. Also, FSTAR is useful in this case because it hides the complexity of the monads. Tuning the verification condition is necessary. Also, sub-affecting is important to alleviate the proof burden, and we think that there is hope this can be practical, that we can take advantage of the SMT automation to not have to prove anything. And for ongoing and future work, we would like to continue tuning to take advantage of the automation. We want to look more into how to verify properties of infinite runs, such as liveness. I showed you what we try to do, but we don't want to use tactics, we want to use automation. To finish the case study, add state and exceptions. And also, this is part of my PhD, that we would like to show, to do some work on secure FSTAR ML interoperability, because we do all this work to verify web server, but then you extract it to your camel and you lose all guarantees, and that's no good. So that will be interesting to do. And also, my advisor asked me to promote that he's hiring. Okay, so that's it. If you have questions.
That's fantastic.